Spontaneous versus stimulated emission. Which one controls the glow of visible light? The answer might surprise you. Okay, so in problem 10 or 11.10, we're now in the emission section of chapter 11. And so what we're talking about here is that we want to find as a mechanism for downward transition from excited to a lesser excited state, spontaneous emission competes with thermal stimulated emission for which blackbody radiation is the source. Show that at room temperature T equals 300 Kelvin, thermal stimulation dominates for frequencies well below, emphasis on this below part, okay, whereas spontaneous emission dominates for frequencies well above. Okay, so below and above is what we're going to need to look at. Okay, so for that then, which mechanism dominates for visible light? Okay, you may have insight on this if you've done modern physics, but we'll see how this comes together all at once. So why do we care? Well, it's because of the emission mechanisms. We're trying to look at what does what and where, okay, not just that it happens. That being said, the challenge for you is what are the three ways light interacts with atoms? Okay, now there's a couple caveats there if you read a couple of papers, but there's three basic ones that we're interested in. That being said, this is a pretty short problem, but the PDF is still available if you want it. Just comment for the link or go to the Patreon page and you'll find it there. Okay, so before we jump into today's topic, you should know that I break things in this complex physics world into more easy to digest pieces. If that sounds like something you'd love, hit the subscribe button and join us in exploring the universe. Let's get started. Okay, so stop number one then. What we have to do is to find the ratio of the spontaneous emission rate A to the thermal emission rate. The reason why we want to do that is because this ratio will help determine which process dominates or if they are equal. Specifically, we will solve for when they are equal to identify a frequency threshold and compare how this balance shifts across different points in the frequency spectrum. So setting the ratio equal to 1 and using the equations that we have, namely the spontaneous emission rate in blue, and then the thermal emission rate in green, which are given by these equations, we can see that we have a lot to go ahead and simplify. But since we're dividing by a fraction, that's the same as multiplying by a reciprocal, so we go ahead and do that. And we see that the script P on both terms cancels. That script P is for the electric dipole, and if you remember from Griffith's electrodynamics, this was the electric dipole radiation. Okay, so naturally, if we're going to have electric dipoles handling this radiation effect, we also have an energy density, which is denoted in purple, and that's from equation 11.59. Okay, but other than that, we see we get a lot of constants canceling, 3 and 3, epsilon naught, h bar, and 1 factor of h bar, but getting rid of that electric dipole, very nice to have, and we'll see in next question why that's such a pain to deal with. Okay, so now we can substitute in the equation of the energy density, excuse me, but we see that that's still in the denominator, so we have to take its reciprocal. Upon doing so, we see that all our constants here cancel out. Omega naught cubed h bar with the omega naught cubed h bar here. Pi squared c cubed, cancel, cancel. Love to see it. So all that we're really left with is this exponential minus 1. And you may remember this exponential if you have taken stat mech because it's the same thing. You have h bar, omega naught, the Boltzmann constant, and the temperature. Okay, so knowing that this was set equal to the ratio and we set it equal to 1, this is our lasting thing. So what we successfully found is the simplification of the ratio, and from this we can find our frequency via omega for some temperature T. Okay, so far, what do you think about this theory? Drop a comment below with your thoughts. I love hearing your interpretations and questions because this will definitely get hairy soon. Let's get to stop 2 where we have the numerics. Alright, so now that we have the ratio simplified and we're left with a relatively easy expression, all things considered, we see that it boils down to just some couple algebra steps. So we take this 1, add this over, we're good to go, that's 2. Take the natural log to get rid of the exponent. We see that we're left with just the arguments. Good to go. Solve for omega, which is multiplied by kBt. See that there, divide by h bar. So we're good to go. But since we're trying to compare here to frequency in terms of the frequency spectrum that we normally deal with, we need to write this in terms of linear frequency. Often we see this as curly F, and that's equal to nu. Okay, nu and V look too similar, so I just put F there just to remind us. And we saw that that was equal to the angular frequency, omega naught, divided by 2 pi. Okay, so now that we have that, we know what omega naught is from right up here, so let's go ahead and put that in our numerator. We see that we have a fraction in the numerator, so that's the same as putting it in the denominator. But let's recall, though, what h bar was, which was the reduced Planck constant. Simplifying this will lead us straight to a numeric easement, so let's get to it. So the reduced Planck constant was h bar over 2 pi. Since we have a 2 pi there, we can just cancel them. And that leads us to a quite easy calculation now. So then numerically, the frequency of interest is putting in Boltzmann's constant for the appropriate units, so joules and Kelvin. Our temperature given was 300 Kelvin. Natural log of 2 came from our ratio. And then we have the Planck's constant down here. So joules and seconds, cancel, 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 cancel. So we're left with 1 over seconds, which goes to hertz. You plugged it into Mathematica or your calculator, and you get 4.328 times 10 to the 12 hertz. Pretty much on par with what we were expecting from the intro part of the question. So we successfully found the frequency. Now we need to write the conclusion statement. And what we realize here is that since the ratio given by A over R is equal to some exponential minus 1, it's simplified to a monotonically increasing function of omega, i.e. if omega keeps going up, then the ratio is going to keep going up. If omega goes down, the ratio goes down. We're not oscillating like with sines and cosines, so that's really good for us in writing the conclusion statement. If this were going down, then we'd have to switch the inequality, which we'll see soon, but because it's monotonically increasing, we're good to go. So because of that monotonically increasing, we can say that frequencies above the threshold that we had for A over R, if we're going above that, we're going to have something greater than 1. And when we go ahead and set up this inequality for greater than 1, we see that A is greater than R, meaning that spontaneous emission dominates. Conversely, for frequencies below the threshold, we see that that's going to be less than 1, so A is less than R, which means that the thermal emissions dominate. And since visible light ranges from 4 times 10 to the 14 to 8 times 10 to the 14 hertz, both of which are well above the threshold, as we recall from the numerics, we can conclude that the spontaneous emission dominates in the visible spectrum. And that's really good to see. Okay. We often think that if I add heat to something a lot, that it's just going to that it's going to lead to the radiation we want. But when we're dealing with the visible light, all the colors we see, things like that, it's a very narrow band of spectrum there. But we see that that is primarily due to the fact that it's visible, so light, so spontaneous emission does make sense. Okay, so we got our conclusion statement. Not that bad of a problem, but definitely something that's going to be tricky when we get to some of the dynamics part of this later in the book. So that's fun. All right. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, there really is, especially in the field theories. And I'd love for you to come along on this journey because it's going to be a lot of fun. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm very grateful for each of you for believing in this journey. So, again, it's been a hectic year. Nothing's been consistent for just about anybody I talk to. So, again, if you can support, that is a blessing, and I thank you tremendously. If you'd like to also join this community, feel free to visit the links in the description below, and then together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.